So yeah, this is my original title, but I decided to make an updated version. So, um, yeah, so before we get started, I like to do a quick poll in the room. So, how many of you think the solar system has ever ejected planets? Raise your hands if you think it is. Okay. How many of you think the solar system has ever ejected Earth mass planet? Okay. Okay, so yeah, I have a good news for you. So today I'm going to present a rogue planet made in our solar system hypothesis for the formation of the outer solar system. So as we all know, the solar system it consists of 8 planets and millions or even billions of small bodies. So these small bodies are the key to understanding the dynamical history of the solar system, and especially their orbital distributions tell you the story of how planets formed and evolved in the ancient past. So far we have discovered 4 major small body reservoirs. So they are the asteroid belt between Mars and Jupiter. There are Jupiter Trojans, which share Jupiter's orbit around the sun. And there are also trans-Neptunian objects, also known as the Kuiper Belt, and the Oort cloud, which hosts long-period comets. Um, though we have so far we discovered millions of small bodies in the inner solar system, but if you account for the mass, the outer solar system, which includes the TNOs and the Oort cloud, should be much, much more massive than our inner solar system. So today I like to focus on trans-Neptunian objects or TNOs in the Kuiper Belt. Specifically, I want to put your focus to a region which I call the distant Kuiper Belt with symmetric axis greater than 50 AU. So in this region, several TNOs populations are hard to explain by existing planet formation models. So we now understand there is a huge population in huge resonant TNOs in mean-motion resonance with Neptunes. So they all the way to 821 and even 921. So there is also the detached population. So these populations show in yellow colors here. So they generally have perihelion around 40 AU, and they're dynamically decoupled from Neptune. So among the detached population, there are a group known as the senoids. So senoids basically means Sedna-like objects. They have very peculiar orbits with low inclinations, very large symmetric axis, and extremely high perihelia. So they all have Q greater than 60 AU, and the orbit of Neptune is only at 30 AU. So it's very challenging to explain them. Another thing that we need to keep in mind is observation bias. So observation bias make it very challenging to discover TNOs with large A, Q, and I. So that's why you only see a few dots in the upper right. That's not because there are just few bodies. It's because it's very, very challenging to detect those objects. But after accounting for the bias, there are at least a factor few more distant TNOs than in the main Kuiper belt. So what a standard or conventional formation model of the outer solar system looks like. Well, first you need a primordial planetesimal belt with estimated mass being 20 Earth mass. So to form the primordial planetesimal belt, um, I'm recently just finished the project with Chris Ormel. We proposed that streaming instability plus pebble accretion could explain the size distribution of the primordial planetesimal belt and all the way to Pluto-sized objects, because that's the largest we observed in the Kuiper belt. So you need a 20 Earth mass planetesimal disk, and you need a planet. Basically, in this case, it's Neptune because it's the outermost planet. Migrate through this planetesimal belt, and during its migration, it will scatter things around. and leaving the Kuiper belt objects implant their Kuiper belt objects to their current location. So in this scenario, it looks more like this. But because there is no other forces in this scenario, there's no other forces other than Neptune's migration, Neptune's scattering. So it's generally very, very challenging to form Sedna-like objects. So these objects tend to have perihelion like from 30 to 40, or maybe sometimes you can get 50, but not Sedna at a Q of 80 AUs. So here I'm showing you a recent simulation carried out by Nils Vorny. So this is their reference model showing you the effect of 4 giant planets plus Neptune migration and plus the galactic tidal force. And you just cannot form VP113 and Sedna. So you need to have some other ideas. So people are talking about stellar flybys, especially when the sun was still in its first cluster, was proposed by Morbidelli. And there are also still existing planet model like Planet 9 or Kuiper belt planet proposed by Patrick. But do we have other idea that could potentially explain the Sedna in our outer solar system? Another idea that better fit the vibe of this room, which is, of course, rogue planets. So yeah, so this idea does not come out of nowhere. Let's inspect some solid evidence in our solar system and beyond our solar system. So first, we have 4 10 Earth mass giant planet cores. And back in 1990s, Alan Stearns suggested there are at least 1,000 Plutos in the early solar system. And now through the Kepler survey, through the transiting planet survey, we now realize super Earth are the most common type of exoplanets. And I just learned from this amazing meeting that free-floating Earth mass planets are also abundant in our galaxy. So we can probably expect 20 per stars. And we all see this great figure by Sumi-san throughout this meeting. So it is thus natural to think that one or more Earth mass objects have formed in the giant planet region and were scattered out, eventually become free-floating planets made in our solar system. If that really happened, the gravity of such a scattered planet, which I just called the rogue, would have affected the Kuiper belt. So in this scenario, if you take into account the lost planet, the formation history of the outer solar system looks more like this. So you still need a primordial planetesimal belt of 20, with the mass being 20 Earth mass, and a bunch of Earth mass planet probably formed in the giant planet region. Some of them are quickly ejected by Jupiter and Saturn. But what if one or more decoupled from Jupiter and Saturn and get recoupled with Neptune and ended up in large semi-major axis? So in this case, the rogue planet, because it's on a large A and highly eccentric orbit, its secular force will start to act on the primordial scattering disk. So through its secular effect, it will very efficiently lift the perihelia of Sedna-like objects and basically forming the senoids. So this process can easily create senoids with Q greater than 60 AU. And as soon as the rogue planet was ejected from our solar system, it will just lift a gigantic icy body population in the outer solar system as we observe today. So here I'm showing you a numerical simulation demonstrating this scenario. So in this simulation, I have a Neptune. It's here. It's initially, it's migrating from 24 to 30 AU. So I put a planetesimal disk with 500,000 test particles. I have a rogue planet with 2 Earth mass with Q at 30 AU, inclination of 15 degrees. So now let me just let the simulation run. So as you can see, because the rogue's Q is still coupled with the giant planets, its typical dynamical lifetime is roughly 100 to 200 million years. And as soon as the rogue was ejected from the solar system, it left behind this gigantic icy body population, which basically covered the entire parameter space of discovered TNO, including the senoids. So here I'm showing the same simulation, but this simulation has been eroded to 4 billion years to better match our current observations. So the icy bodies created by the rogue tend to have low inclinations, like less than 30 degrees, and very high perihelia and semi-major axis. Okay, so I just show you, okay, there could be an ejected planet in our early solar system, but how do you know, how do you verify or falsify this hypothesis? It's not like I'm going to find this rogue planet ejected 4 billion years ago. There's just no way, like even with microlensing survey, you cannot find the lost planet 4 billion years ago. But I discovered something during my study, which can be used to verify and falsify this hypothesis. It's called primordial orbital alignments. So just like I explained, the rogue lifts the perihelia of TNOs through its secular effect. And because the rogue planet has a very eccentric orbit, its orbit it has large eccentricity, this perihelion Q lifting effect will only happens close to the rogue's own apsidal lines. So which means if there's another object looks like this, it will not get Q lifted. So because of that, if senoids were indeed produced by the rogue planet, their apsidal line 4.5 billion years ago should have clustered, right? So if you think the rogue planet really did the job, if you back integrate all the senoids back to 4 billion years ago, you should see a strong clustering in longitude of perihelion. So therefore, I carry out backward numerical integration of the 3 senoids, taking into account the gravities of the 4 giant planets and the galactic tides. I use the Mercurius integrator in the rebound package, and I use the SB Dint, which is a tool to create TN clones developed by Spencer Volk, Volk. So next, I'm going to show you an animation of this backward integration. So let's just rewind time for the 3 senoids. And very surprisingly, you just see their apsidal lines align with each other 4.5 billion years ago. And this is my honest reaction when first seeing this alignment. I was basically mind blown by this discovery. Okay, so of course you need to. There's some caveat because one of the objects has really large semi-major axis and still large orbital uncertainty. The orbital uncertainty also bring numerical bring uncertainties to the backward integration, so you have to take into account. But if you only focus on their median orbit, the only time the senoid apsidal lines were clusters was around 4.5 billion years ago, with the secular variance being 10 degree. So this primordial orbital alignment is independent of any observational biases that contribute to the current on-sky clustering in the large A Kuiper belt. In other words, this discovery is fundamentally different from theories like Planet 9, which suggest the current clustering among the distant TNOs. So now let's let's look at the how Rogue lifted the senoids in another parameter space. So here the horizontal axis is the omega, the longitudinal perihelion, and this is Q. and the yellow line shows you the rogue planet's own epsilon line. You can see like during 200 million year or so temporary presence, the rogue planet produced a strong alignment in the longitudinal perihelion close to its own epsilon line. As soon as the rogue was ejected, the dynamics also changed. The primordial detached TNOs start to precess in different rates due to they have different symmetry axis and Q, leading to a more uniform distribution to today's longitudes. However, there is an exception to this uniformity which exists only beyond Q greater than 120 AUs. But it's with current telescope, it's almost impossible to discover the Q greater than 100 AU objects. But if we have more future senoid discovery, we can do the same analysis and integrate them back to verify or falsify this hypothesis. So how about stellar flyby? Could this stellar flyby also create the primordial clustering? So to verify this, I carry out one stellar flyby simulation with this given parameters. So the blue dots show you a primordial scattering disk, and this red dots show the passing stars. And let's focus on this panel. This panel shows you the Q versus omega. And basically, although stellar flyby explains senoids in the AQ space, it does not create any clustering or alignment in the omega space. I further collaborated with Hu Qingru from Tsinghua University. So she went a step further, carry out thousands of stellar flyby simulation with different injection angles, velocities, and impact parameters, confirmed the finding that the stellar flyby models are very unlikely to produce the primordial alignment among senoids. Okay, so there is another thing we can compare the two different hypotheses, the rogue versus stellar flyby. Just as I mentioned before, the rogue planet tend to create a very moderate inclination distribution with the vast majority objects having QI less than 30, whereas stellar flyby can very easily hit the inclination distribution of these objects and easily create even retrograde senoids in the outer solar system belt. But that's so far we haven't discovered any retrograde senoids yet. So here is my summary slides. I think I'll just leave the slides here, and yeah, happy to answer your question. Thank you.
It's interesting the way you get the alignment when you rewind that set.
Yeah.
Yeah. So I guess LSSD will give you more to test that with.
Yeah, exactly.
All right. So my question is, how big a role did the galactic tide play when you rewind this? Just because there's a lot of uncertainty of the sun's galactic position in time.
Yeah, that's a very good question. So the galactic tides, so strong now, like it's how do I say this? It's like so because they have different orbits. They have the three senoids we discovered today are at A of 200 AU, 500 AU, and 1000 AU. And the galactic tides will influence the outermost objects more strongly. So in this case, the galactic tides is able to also to make the perihelion of the outermost objects oscillate, but it's not going to it will increase the error bar of the backward integration, but galactic tides itself will not induce will not add additional precession force to the senoid's secular evolutions. So yeah, I verified that. I think I have a backup slides showing you just that. Yeah, so yeah, this is like Do you see this? Yeah. So this is Lelea Kuhonua, which is the outermost objects. Integration with galactides and without galactides. So the blue line is without, and the red line is with. So with the galactides, it creates these Q oscillations, but it only slightly increase the omega uncertainties. So yeah. Yeah.
So you looked at how much does this depend on there just staying on road? So when we see amount stuff, if there's say 2 Earth mass planets or 3 or 4 Earth mass planets on the way out.
Yeah, so that's a good question. So there's some. So I think with the current, with our current best understanding of the Kuiper belt, if you consider if one rogue planet can well explain the formation of the outer solar system, maybe we should not consider more because okay, so there is this what's it called Alchem's razor, which means like if a simpler model can explain the one things already, you don't need to add layers to that model. So I think one rogue planet can already well account for the formation of the outer system, but that doesn't mean the solar system only ejected one Earth mass planet because most of them could only existed in the outer solar system for maybe less than 1 million years. And these rogue planets would not have dramatic, significant impact on the orbital distribution of senoids. Only the temporarily present one, by temporarily present, I mean 100 million years or so, can leave a observable trace in the outer solar system. So my study is like focusing on the rogue that has the dominant effect that survives longer in the outer solar system, basically.
Yeah, maybe it's likely there's another scenario. Just curious if the mechanism maybe.
So if 2 of them are both present in the by present I mean like survive there for 100 million years, that would probably create 2 peaks instead of 1 peaks in the Senoid population. And once we get more data, it's easier to verify the true distribution of Senoids.
I saw your simulation also simulates whole Kuiper belt. So I'm curious, does your simulation like in the Kuiper belt, does your simulation fit in the Kuiper belt because we have more data about it?
Yeah, this is the slide that answer your question. So here I basically put my model into a survey simulator. The gray dots are the data, are the simulation results from the rogue planet model. I use a survey simulator to create a simulated detection and compare it with the real well TNOs, which are showing black. So you can see like in semi-major axis, perihelion and eccentricity, the black and red line, which just match each other pretty well. So it does create the Kuiper belt we see today.
So you assume that the rogue planet is eventually ejected?
Yeah, that's the most likely scenario.
Oh yeah. Then no more also eccentricity. So why the alignment with the differential precision may occur in a long time scale?
Yeah, so the alignment was not preserved. So I have where is it? Okay, so this figure. So the left panel shows the omega distribution of omega at the rogue's removal, which is maybe 4 billion years ago. And the right panel shows the current day distribution. So the differential equation can quickly uniformize the Omega's distribution for Q less than 120 AU. So only for Q greater than 120 AU, if such TNO really exists, the alignment will be preserved.
Only a small fraction.
Yeah, yeah, and these small fractions are very hard to observe.
Oh, okay.
Yeah.
All right, I have a final fun question for you.
Yeah.
So what is the ejection velocity? And if you multiply that by 4 billion years, how far away is this thing?
The ejection velocity should be just the typical ejection velocity for small bodies. That could be, I think, less than 1 kilometer per second with respect to the solar system. Since the solar system had already like orbited the galaxy for how many circles? Like more than 10 circles. It's almost impossible to trace the location of the lost planets. Is that your question?
Oh, I just, what is half a kilometer per second times 4 billion years? I don't even
Okay, half. Let's just call it 1 kilometer per second. 1 kilometer per second is 1 parsec per million year. Okay, so that gives you 4,000 parsec.
So it's really far away.
Yeah, yeah.
Okay, we'll move on to our final talk before lunch.